Namaste and welcome to the lecture on linear algebra through geometry. In the last lecture we looked at the idea of vector spaces and idea of subspaces, and towards the end of the class we also had a couple of exercise problems where I had asked you to check if given set of vectors would actually form a vector subspace or not. So we will just quickly have the answers for this. Like in this case the first one, if you look at the set of the vectors basically x1 comma 2, this is basically a line with the second coordinate fixed, which means it is going to be a line which is parallel to my horizontal axis, and therefore this line is not a line which passes through the origin, therefore this is not a subspace. The answer is no. In the next case we had A2 cross 2 is a set of all invertible 2 by 2 real matrices, then check if A 2 by 2 is a subspace of M2 by 2, which is a set of all real matrices, and here also it will fail because we will get the 0 matrix in this case. Suppose you just take one of the 2 by 2 matrices to be the let us say identity matrix, and then you subtract the identity matrix from itself, then you get the 0 matrix. The 0 matrix is not an invertible matrix, therefore the answer is no here. In the third case what we have is we basically have the set of vectors where in which all the 3 coordinates are basically greater than or equal to 0. This will essentially boil down, if you take in R2 this would correspond to x1 greater than or equal to 0, x2 greater than or equal to 0, basically your first quadrant. If you do a scalar multiplication of these vectors and you use a negative scalar, you will not find those vectors, here. That means if you use a negative scalar, it will not be closed under your scalar multiplication. The set is not closed under scalar multiplication, and therefore in that case we are going to say that this is not a vector space. So all 3 examples that we took basically are not vector spaces, right. So in today's class what we are going to do is we are going to move ahead and look at the notion of linear combination of vectors, which we have already studied in 2 dimension and in 3 dimension, but we just want to generalize it to n dimension. So we want to look at the idea of linear combination of vectors in n dimension, and we are going to look at what is it to say a linearly independent set of vectors basically in a higher dimension, like how are we going to do it, what is the, we are going to have a proper mathematical definition for the same, and then we follow it with the idea of basis and dimension of a vector space, so or a vector space or a subspace. So that will be the agenda for the next 2 classes. So in this class we are going to look at the idea of linear combination of vectors in n dimensional space and linear independence. So let us go ahead. Okay. So suppose let us assume that, so we are going to always have this in mind, like I am going to look at Rn, that means every vector here is going to be an n component vector. So let us say any vector in Rn implies you have is basically defined by this x1, x2 etc xn. So this is what we have. So basically what we see is this a vector, like how we had in case of 2 dimension, a vector was basically an ordered pair of 2 numbers, 2 real numbers. In this case we are going to call every vector is basically an ordered n tuple of real numbers, ordered n tuple of real numbers. So what are we going to do? We are going to look at linear combination like the way what we did in 2 dimension and 3 dimension. So what we do is let us define certain vectors, let u1 be a vector which is defined as, let us say u11, u21 etc un1, then I am going to have this vector uk1 the vector uk, which is basically given by u1k, u2k etc unk, which basically says that these are all vectors, k vectors which are n dimensional. That means each vector has n components. So, we are going to say that these are all n component vectors and there are k such vectors here, right. So, suppose we say that there exists a vector, suppose we have let u be a vector defined as, let us say again it is an n component vector, let us say u1 etc. Okay, that will be a problem. Okay, that is another. Okay, let me make this, let v be any vector given by so where the vector v is basically, let us say v1 v2 etc. vn, n component vectors. Now, we say that the vector v is a linear combination of the vectors u1 to uk, combination of the vectors u1 etc. uk if and only if there exists, let us say real scalars alpha 1, alpha 2 etc. alpha k such that the vector v can be written as alpha 1 u1 plus alpha 2 u2 plus etc. plus alpha k uk. If we are able to find out scalars, then we say that scalars alpha 1 alpha 2, real scalars alpha 1 alpha 2 alpha k, then we say v is a vector which is a linear combination of vectors u1 to uk, right. Now, I mean, where do we apply? In fact, if you look at the textbook on applied linear algebra by Stephen Boyd, he very nicely gives a very interesting application. The book titled as Applied Linear Algebra by Stephen Boyd. And others. He gives the linear combination of the vectors. A very good example that he gives is basically the following. He says that suppose, so the example is basically, I mean the example that we have looked at is basically from this reference textbook Applied Linear Algebra by Stephen Boyd and others. Suppose u1, u2 etc. uk correspond to different audio tracks, taken over the same period of time. For example, say that u1 is a voice signal, then u2 is basically say some let us say a violin etc., and you define your u2 uk etc. so on. The final music track that we get u is basically, let us say alpha 1 u1 plus alpha 2 u2 plus etc. plus alpha k uk. This represents the mixture of audio signals, mixtured, basically it is a mix that we have, mixture of audio signals or audio tracks where the alpha i's it corresponds to the relative loudness for each of the tracks, relative loudness. So, it is interesting to see that linear combination of vectors, what we see in terms of vectors actually has an application where we see that if you look at different audio tracks and then you want to combine them with individual loudness. So, the resulting signal that you get finally is basically is a mixture of all these audio tracks, which is essentially a linear combination. This is what it is, right. Okay. Now, let us check, how do we check whether a given vector is basically a linear combination of the set of vectors or not. So, we already saw one of the examples. Let us look at the same case example. Check if the vector u is equal to 2 0 4, this was the one that we took yesterday, is a linear combination of the two vectors u1, which is given by 1 1 2, and the vector u2 is equal to 1 minus 1 1. Now, what we want to do is we want to find out scalars. So, what is it to do? We say solution is basically to find scalars alpha 1 alpha 2 such that alpha 1 alpha 2 real scalars such that u is equal to alpha 1 u1 plus alpha 2 u2. This is what we have. So, what we do first of all, construct a matrix A where in which you put these two vectors, let us say u1 and u2. So, I will take 1 1 2 and then 1 minus 1 1. So, this becomes the matrix A. I just take the two, here we have these two vectors. So, if you have n vectors, you put those n vectors as the columns of the matrix A, and then what you do is we want to check if Ax is equal to B has a solution for this corresponding B and the given A. That means, where the X matrix is going to be my alpha 1 and alpha 2 and the B vector is going to be 2 0 4. So, we already know if you try to do the row reduced echelon form for this of A augmented with B, we get something, we get very interesting. We have this 1 1 2 1 minus 1 1, you augment it with the B matrix, which is B vector, which is basically 2 0 4. Now, here we can see that we can take R2. So, if you follow the steps, R2 to R2 is R2 minus R1 and R3 is R3 minus 2 R1, we get the following. We get this matrix, which is basically 1 1 2 0 minus 2 minus 2 0 minus 1 0. Again we do R3 is equal to R3 minus R2 by 2. So, we end up getting this, we get 1 1 0 minus 2 0 0, and this we have 2 minus 2 4. And what we see here is there is an inconsistency here. The 0 row on the left hand side has a non-zero element on the right hand side. So, this is basically inconsistent, and therefore, we say that there is no solution. So, this corresponds to no solution. That means, we cannot find no alpha 1 and alpha 2 exists satisfying the three equations. Therefore, we say that the vector B is equal to 2 0 4 cannot be expressed as a linear combination of u1 is equal to this vector. What was that vector? 1 1 2, and u2 is basically this vector, which is 1 minus 1 1. So, that means this B vector cannot be expressed as a linear combination of the two vectors, say u1 and u2, that is what it is, right. Okay. Now, given a set of vectors, we also had in the past when we discussed, given a set of vectors, we were also looking at the idea of linear independence. So, let us look at the notion of linear independence in higher dimensional vector space. So, let us look at this. So, let us get into the idea of linear independence. Now, what do we mean by this? Given a set of vectors, given let us say the vectors u1, u2, etc., un, all vectors of Rn, elements of Rn, right. We ask this question: what is the linear combination that gives, what is the linear combination of these vectors that gives the 0 vector? Zero vector again in Rn, that means you will have n component 0 vector. So, this is the question that we want to answer. Now, if we get there is only one combination which is going to give me the 0 vector, that means what are we trying to look for? We are trying to look for the following, we are trying to look for, what does this mean? This means suppose I write 0 vector is equal to alpha 1 u1 plus alpha 2 u2 plus etc., plus alpha n un. These are vectors that we have. What are the values for the scalars? What are the values of the scalars? Right, that is a question that we ask, and the answer to this is going to tell us whether the given set of vectors, say u1, u2, un, are going to be linearly independent vectors or not. Yeah, okay, let us look at this. So, what we do for that? We are going to look at formal definition, and then let us get ahead. Okay, we are going to have a definition. So, let S be the set which contains this vectors, let us say u1, u2, etc., let us say un. We already said it is a set which contains this. So, we say be a non-empty subset of Rn, here it can be a non-empty subset of any vector space. Right now I am choosing the vector space to be Rn. So, it could be a non-empty subset of any vector space. So, okay, let us look at this. So, the set is linearly independent. So, we are going to define this. The set S is linearly independent set if and only if there exists real scalars say alpha 1 to alpha n, such that the equation alpha 1 u1 plus alpha 2 u2 plus etc., plus alpha n un is equal to the 0 vector implies alpha 1 is equal to alpha 2 is equal to etc., equal to alpha n is equal to 0. That means all the scalars are 0. Right, the scalars are 0. that is the only linear combination. So, how do we interpret this? The only linear combination, what do we mean by that? The only linear combination that gives the 0 vector is the trivial linear combination with scalars is equal to 0. In case if there exists at least one non-zero scalar, one alpha I not equal to 0, then the set S is a linearly dependent set. Right. If you have a set of vectors, the only linear combination which gives the 0 vector must be the combination where which the scalars must be 0. That means you are going to look at a set of non-zero vectors. Whenever there is a 0 vector that is there in the set actually becomes a linearly dependent set, because you can put all the other scalar to be 0 and the scalar corresponding to the 0 vector you can make it any real number, it would still give you a 0 vector. Therefore, let us make this comment. So, what we do is we are going to say, note, any set that contains the 0 vector, the 0 vector is a linearly dependent set. Is that okay? It is a linearly dependent set. Now, we have already seen that in 2 dimension, I mean if you just take 2 vectors in R2, the 2 vectors are linearly dependent if one is going to be the scalar multiple of the other, right. So, what are we going to say? We are going to say that so any subset or any subset, okay, let us write this. In fact, let's make it very clear. Any subset of a vector space, any subset of a vector space V which contains the 0 vector is a linearly dependent set. So, that is something which we need to remember. So, the question is, how do we check whether what do you say, how do we check whether the set of vectors is linearly dependent or independent? We will come to it in a bit, but before that let us make one more important observation 2. Suppose let us say the vector u is a linear combination of the vectors u1, u2 etc., let us say un, where all these vectors are basically all of them are in Rn, okay. Set of the vectors in Rn, then that means we can write the vector u to be equal to alpha 1 u1 plus alpha 2 u2 plus etc. plus alpha n un, right, basically the linear combination of these vectors. Now, what we are going to do is we are going to consider this case when u1 u2 uk or un, when u1 u2 etc. un is a linearly independent set, then we say that the vector u can be expressed, can be uniquely expressed, or can be expressed uniquely as a linear okay, let me put this, can be expressed as a unique linear combination, as a unique linear combination of u1 etc. un. Now what does that mean? That means if you have u1, u2, un to be linearly independent vectors and you want to express any other vector as a linear combination of these vectors u1, u2, un, there exists only one combination, that means one set of scalars alpha 1, alpha 2, alpha n, such that alpha 1 u1 plus alpha 2 u2 plus alpha n un is equal to the given vector, let us say u. There does not exist any other representation for this. That means the representation of the vector u in terms of these linearly independent set vectors is unique, because the set of scalars that you get is just a unique set of scalars. There exists no other scalars which is going to give which is with which you are going to get the vector u as a linear combination of this vector. So that is what these set of vectors u1 to un. So how do we do this? Let us quickly look at a small proof, we will understand it better. So what we are going to do is we say, suppose there exist two combinations, exist two linear combinations for u in terms of the linearly independent vectors, the linearly independent vectors u1 to un, let us say we have two sets of scalars, namely the vector u is equal to alpha 1 u1 plus etc. plus alpha n un. Similarly, this is also the same as beta 1 u1 plus etc. plus beta n un, because we said there are two linear combinations, one is in terms of the scalars alpha, the other one in terms of the scalars beta. Assume that I mean, since they are unique, alpha 1 is not equal to beta 1, alpha 2 is not equal to beta 2, and alpha n is not equal to beta n. So this is, I mean, this is what we are going to have. So what we do is you just subtract, if you subtract these two guys, what are we going to get? We are going to get the subtracting, we get this is also the u vector subtracting, let us call this as 1 and let us call this as 2, 2 from 1. What do we get? We get the 0 vector on the left hand side, which says, which is equal to beta 1 alpha 1 minus beta 1 into u1 plus etc. plus alpha n minus beta n un, and this is going to be a contradiction to the fact that the set of vectors is a linearly independent vectors, because alpha 1 minus beta 1 is going to be a non-zero scalar, alpha 2 minus beta 2 is going to be a non-zero scalar, alpha n minus beta n is also going to be a non-zero scalar, as in which case we are going to have different scalars, let us say gamma 1 u1 plus etc. plus gamma n un, we are going to have this. Now you see that if the set of vectors is linearly independent, the only way in which can happen is gamma 1 is equal to 0, gamma n is equal to 0, gamma 2 is equal to 0, all gammas to be equal to 0. But in this case, since alpha 1 is different, beta 1 is different, the combination is going to give a gamma 1 which is a non-zero scalar which is going to give this. Therefore, this becomes a contradiction to our assumption that it is a linearly independent set. Therefore, what we are going to see, this contradicts the fact, this contradicts the fact that u1, u2 etc. un are linearly independent, right, but we have already taken them to be linearly independent. Therefore, the only thing that is possible is, therefore, all coefficients gamma i's must be 0 for all i's, for all I is equal to 1 to n. Therefore, alpha 1 minus beta 1 must be equal to 0, alpha 2 minus beta 2 is equal to 0, etc. Alpha n minus beta n is equal to 0, which implies alpha I is equal to beta I for I is equal to 1 to n, right. Therefore, this implies there exists let us write this. So, this implies if u1, u2, etc., un are linearly independent vectors in Rn, then for every u in Rn, every u vector in Rn, there is a unique linear combination of u1, u2, etc., un, right. There is a unique linear combination in terms of u1, u2, un. We can prove the converse also. What we do is, if you take this be the set of all linearly, I mean you say that let S be the set of all possible vectors which can be uniquely expressed as a linear combination of say u1 to un. We also have the 0 vector which is expressed as 0 times u1 plus 0 times u2 plus etc., 0 times un, which is going to give you the 0 vector. And if you say a1 u1 plus a2 u2 plus an un is equal to 0 vector, then naturally a1 is equal to 0, a2 is equal to 0, an is equal to 0. Therefore, you have the vectors to be u1, u2, un to be linearly independent. So, you can prove converse also. Okay. I will just leave that as an exercise where you can prove converse of this. So, let us make a couple of statements before we get on to something else. So, a set of 2 vectors, in Rn is linearly dependent set, So, LD I have actually used this before, linearly dependent set if one of the vectors, one of them is a multiple of the other. And we are going to make one more interesting observation, and what is that? A set that contains only one vector only one non-zero vector is a linearly independent set. This is you can verify it on your own. It is a non-zero vector. So, in order to get a 0 vector, all the set of vectors can only be the linear combination of this single vector can only be the multiples of this vector, and the only multiple which is going to give me the 0 vector is basically by taking the scalar to be 0. So, that is something which we can look at it, right. So, that is easy to do. So, how do we check a given set of vectors is linearly independent or not? So, how do we check? If given set of vectors is linearly independent or not, there are multiple ways in which we can do. One way to do is define a matrix which contains A whose columns are the given vectors, whose columns are the given vectors Now what we do is we want to find out whether the vectors are linearly independent or not. So now solve the homogeneous system of equation Ax is equal to 0. Homogeneous system of equations Ax is equal to 0. If we get trivial solution, only trivial solution, then the vectors are linearly independent. If you get a non-trivial solution, the vectors are linearly dependent. Linearly dependent, right. In fact, we can verify for the example that we took where u1 is equal to, we had this 1 1 2 and u2 is equal to 1 minus 1 1. We did the same thing, we populate the matrix, we had this matrix A which was basically 1 1 2 1 minus 1 1. Now you solve Ax is equal to 0. We will see that x1 is equal to 0, x2 is equal to 0 is the only solution that we get, and therefore these two vectors are linearly independent. That is what it is. Now where do we go from here? What do we do? I mean, the moment you have a set of linearly independent vectors, what is it that we can do with this set of linearly independent vectors? Suppose I have a set of, let us say, n linearly independent vectors. Can I get what am I trying to look for is basically, is it possible I have a set of k linearly independent vectors, let us not look at n, suppose I have a set of k linearly independent vectors, what is the set of all possible linear combinations of these k linearly independent vectors going to give us? That is a question that we want to answer, and if it gives if suppose I have a set of vectors and the let us say linearly independent vectors, I have a set of linearly independent vectors and the set of all possible linear combinations, will it form of this set of linearly independent vectors, will it form a vector space? If that is the case, these linearly independent vectors can be used as generators for vector spaces. That means you can look at them as the linear combinations of them is going to generate all possible vectors in the vector space. Then in that case we have some name for it, and so what we will do is in the next lecture we will look at the set of all possible linear combinations of a given set of vectors, and then we will get into the idea of what is known as basis for a vector space, and then we look at the idea of dimensions for a vector space. So in this class what we did, we basically looked at the idea of linear combinations of n component vectors, and in specific we wanted to look at what is that linear combination of n component vector which is going to give me the 0 vector. Suppose if I have a set of vectors where in which the only linear combination which gives me the 0 vector is basically with the scalars being 0, then we call such a set of vectors to be linearly independent set of vectors, and whenever there is a non-zero scalar that exists which is going to give me a 0 vector, then we said the set of vectors is linearly dependent. And therefore we also came to a conclusion that any set of a vector, any subset of a vector space, non-empty subset of a vector space which contains the 0 vector is definitely a linearly dependent set, because all the other vectors you can put the scalars to be 0, and for this particular 0 vector you can put any real value and that is going to give you a 0 vector, which means we are going to get a non-trivial combination, linear combination which is going to give us the 0 vector, and therefore the set of vectors is going to be linearly dependent. And how do we check whether a set of vectors is linearly dependent or not? You put that set of vectors in a matrix and solve the system of homogeneous system of equation Ax equal to 0. If the trivial solution is the only solution that you get to this homogeneous system of equation, we end up saying that the vectors are linearly independent. the vectors which form the columns of the matrix are linearly independent. If not, you say that the vectors are linearly dependent. So, in the next class we will look at the idea of basis and dimension of a vector space. Thank you.